I'm going to start with, we've already heard some talks on some aspects of this. I'm going to try not to repeat what has gone before and what will probably come after, looking at the titles, but there'll probably be some. I'm going to talk about some general categorization, or overly general categorization of magnetosphere-ionosphere coupling. I'm going to sort of distinguish magnetic versus non-magnetic bodies. I'll probably emphasize this, since there are going to be quite a few on the, we've heard about Earth, we've heard about Mercury, we'll hear a lot about Jupiter and Saturn, so I'll say something about this, but I want to distinguish them some, and I'll hit just some examples. Probably more Venus and Titan in this particular talk. So it's one of these gross generalizations. There are Earth-like interactions, planets which have significant intrinsic magnetic fields, and what counts as relative to other things. I mean, Mercury, although it's not as large as Jupiter, Earth, it plays the dominant role in the interaction. Earth, Jupiter, Saturn, the outer planets, Ganymede would go in that category. Things where that, might say, intrinsic field would play a role in as acting as an obstacle to the solar wind flow. On the other hand, Venus has no intrinsic, well, has to have something, but it's not measurable at the moment. Let's put it that way. It takes the ionospheric thermal pressures thought to play the main role in acting as an obstacle, basically NKT. Comet-like, where what we heard from that from Andrew Coates, is the ion pickup probably plays the dominant role, mass loading. Ions are born in this very extensive atmosphere. They're picked up. They slow down the flow. There is a weak, very weak shock, and then that will dominate. Now, of course, real interactions are not so simple. They sort of probably have a little of all of these in different parts of different regions. For example, particularly for Mars, Mars really does. All three do play a pretty close role. Earth mainly, that. Comets are mainly comet-like, but they all have different aspects. So, again, I will not linger on this. We've been hearing about this all week. We'll continue to hear about it. But to point out, here is the Earth's, no bow shock on this one, right here. It's this field right here. Call it B squared over 2 mu naught, holding off, if you wish, the solar wind pressure. And, of course, many details. Closed or open. That's the dominant zeroth order thing. Now, of course, different details, if it's northward or southward IMF, what happens to the interior dynamics. It depends on, obviously, the connection to the solar wind along open field lines, and there's a whole system of currents. So the magnetospheric dynamics in here, though, even that is dominated by or organized by the intrinsic field. So the intrinsic field and all of these aspects of it that we've been hearing do very much depend on that strong intrinsic magnetic field, in addition to induced fields associated with these current systems. Also, what we've been hearing about is how a lot of these current systems link up with field line currents to the ionosphere and the role of ionospheric conductivity. So the question will then be, what happens to non-magnetic bodies where we don't have this field? So let me take an oversimplified way of looking at some of this dynamics by just looking at a single fluid MHD equation, which is often not appropriate, but we won't go there, particularly in the ionosphere where you really want to work with the individual momentum equations, but just for the sake of discussion. So the role of field line occurrence is linking the dynamics in two different regions, two different plasma environments. For example, current in one region is needed to balance momentum, and the current then closes in another region, for example, the ionosphere. And if we have a strong intrinsic field, that will organize how this happens. So if we take this simple, if you wish, Newton's second law for a plasma parcel, mass times acceleration is equal to different forces. Pressure gradient force, the Lorentz force, or J cross B force, gravity, and what terms are important depends where you are. Ion neutral collisions or friction, mass loading. If you're at comets, this is important. If you're out in the way out in the magnetosphere, you don't need to worry about these two, but these will be important. So it depends where you are. Or you'll need something a little more sophisticated if you have parallel and perpendicular pressures. If you're down in the ionosphere, you'll need the friction, you'll still have J cross B, and you'll have gravity. So if you'll have different versions of this in different regions, which would then be linked by field line currents. Now, you also hear about a lot of auroral emission, mostly electron precipitation. That will be an issue. I'll talk about that at the very end of the session, because it's often hard to, and this is upward current, it's often difficult to see upward current, which I think is an issue on Jupiter and other. So I'm not going to go into this because you'll hear a lot of this, and I'm going to go to non-magnetic planet, but typically you worry about the magnetospheric dynamics, the J cross B forces. You can then worry about what parallel currents it does. Then you go down to the ionosphere, you link the two, somehow you go from here down to the ionosphere, and then worry about the dynamics down there, and worry with the Peterson-Hall conductivities, and you have to worry about what the neutral winds are, and dynamos and stuff. And again, you will use this as a diagnostic in many cases, at least for the upward current, due to that auroral emission. Okay, and again, we'll hear about that. Now so let's just look, if we do have a large intrinsic field, we have two regions, whether it's Earth's field or Jupiter. You could say that there is might say a rapidly flowing dynamical region where collisions are not important. For example, you have a rapid flow of plasma, say from left to right up here, due to some other forcing. Who knows? Pressure, you name it, okay? This could be the solar wind, could be in the plasma sheath. I mean, this is always not the simple geometry. Stretch these out and move this slab way over there. And then down here, you've got a bottom plasma slab stuck into the neutral gas. So if you're pushing this around, you'll generate J cross B forces from the bending of the fields, and which will try to impede this. That, if you look on the side of this, these slabs are not infinite. The current will want to close, go down from the top slab to the bottom, along this, quote, large intrinsic field, by this field line current, and then try to accelerate the plasma in the lower slab. Of course, the neutrals resist, hence, Peterson conductivities, and the two are thus linked. Or, of course, you could do it the other way. I mean, maybe something happens down there to change dynamics, and the currents will flip and go the other way. But they're linked. That's one type of linking. Another type of linking is really not due to this more shear type thing. You could have compressional linking, which actually happens perpendicular to the magnetic field. So that would be needed to complete the picture, is the compressional type linkage. Now, at a Earth-type planet, these stresses will be near the magnetopause boundary, in the tail, in the subsheets, where you have reconnection on the day side, all different type stresses, which will then generate region 1, region 2 currents. These will try to close in the ionosphere. That'll affect their development. We've been hearing about these nonlinear couplings. And the solar-driven things are very important due to that reconnection. What we'll hear from Tom Hill tomorrow, and we've already heard a little bit, at Jupiter-like, or Saturn-like, and they're not quite the same, the rotational effects dominate. So they're like this plastosphere on steroids, basically, where basically the collisions, Margie was talking about this, moving what keeps the thing rotating as you go out there. So it'll be co-rotational electric field, it'll go out, all's well and fine, it'll move it unless something tries to inhibit it. Like you're adding more plasma, as in Io Taurus. Or the plasma's trying to move out and the co-rotation can't keep up with it. Then you could say, well, gosh, I need a J cross B force. That'll have to close. Current goes down, current goes up. The ionosphere will resist it. That J cross B will go the opposite way. It'll drag you down. Of course, if you have a rapid neutral wind, you could then change things and it goes back up again the other way. Now, what you see here on Jupiter is actually not this distance. It's out at about 30 Jovian radii. So this is not at all to scale. And what you're diagnosing with the main auroral oval is going out to 30 RJ is right here, is the upward field line current, the electron aurora. These 100 keV electrons, 100 megaamps, okay, is what's doing it. The issue and discuss, not now, but at the last talk, is what happens up in the polar cap. That is less well known, and I'm not sure I'm going to shed that much light on it, but I'm going to at least indicated diagnostic tool that one wants to pay attention to when you are trying to shed light on it. Okay, what about the weakly magnetized objects? What's the magnetosphere? Well, there's a, quote, induced magnetosphere, sort of a poor man's magnetosphere, okay? There's been definitely ionospheres in most of these things, except Mercury. Okay, so we want, Mercury's not going to be discussed. So we could try to generalize and see if we could use this type picture. So we get two plasma regions connected by a magnetic field. Even if it is predominantly induced magnetic field, it's still connected. One is neutral dominated with plasma, the other is hotter, less dense, and faster plasma, like the solar wind flow past the Venus ionosphere. So we could still, quote, call that magnetospheric-ionosphere coupling if we're very loose and just say, hey, we'll call the solar wind the magnetosphere, or whatever the other region is. Now, what are the issues with the MI coupling at magnetized object? Well, the same thing, weakly magnetized. Same thing as it is at magnetized. We worry about transfer of particles, momentum, and energy between the two regions. Particle inputs are important. Electrons might only be just solar wind electrons. The diffuse type aurora will come down and contribute to ionization. And plasma. Ions could go out the field line, like we heard from Joe Westlake's talk, out into Saturn's magnetosphere, or out the tail of Mars, or out the tail of Venus. Force and momentum balance, the sort of thing I've been emphasizing up to now. There's pressure balance at the ionosphere and solar wind. Perpendicular, that is just mainly just compressional pressure balance. But there could be things along the field line too, linked with field line currents. This then affects the dynamical flow of the plasma in the ionosphere. Is often strongly affected by that external region. If somehow you could get the momentum down into that ionosphere. And then energy exchange. Particles are coming in, they carry energy. Particles going out, you lose energy. The electron temperature calculations you need for things like Venus and Mars do require an energy input along the field lines by superthermal electrons or something. Now, the bookkeeping you want to do differently, though. And you have a strong intrinsic field, you can bookkeep current. In this case, you want to bookkeep all in the magnetic field, so you use Ampere's law, get rid of the current, and you've got MHD or MHD codes. Well, even for the strong terrestrial-like planets, MHD codes are used. They're just not brought all the way down to the ionosphere. They're linked somehow at some boundary at 3 planetary radii or something. But in the non-magnetic planets, you want to use the MHD approach everywhere. You don't want to talk about really Peterson-Hall conductivities with these induced fields. It doesn't make sense. And the fields are sometimes very topologically complex, as in Titan. You just get yourself confused. So you shove that into that momentum equation I showed earlier. Now, for some very simple conditions, like at the Venus ionopause, then it's sort of quasi-static, and all the pressures, electron and ion, magnetic pressure, right here, will balance. So now some quick examples, since I'll run out. Oh, and you still need another equation if you're going to use the MHD approach, so you use Faraday's law. Okay, Venus. Some old figure, but still very relevant. Here's the solar wind to the left, comes in, bow shock, field piles up, thermal pressure converted to magnetic pressure in the cushion, and then a sharp boundary, sometimes sharp boundary, I should say, between this hot solar wind flowing plasma, magnetized, and in relatively low solar wind dynamic conditions in solar max, this region is cold, relatively slow, and the obstacle is that pressure balance between the two. But nonetheless, on other occasions when the solar wind dynamic pressure is higher, this field will push right through the whole ionosphere and destroy it, which allows this to be inlets for electrons, outlets for ions, and certainly down the tail there is outlets and loss of plasma. Similar type diagram you could draw for Mars, Titan, etc. All these sort of weakly magnetized things. Loss of plasma, input of plasma, and energy. Main momentum balance is compressional there, but you will have situations where you will have field line currents and you'll have some dragging due to the curvature forces in there as well. But you're not bookkeeping on one, might say, dynamo-driven intrinsic field when you do these things. You do an MHD. Just focus on the left. I love this picture, been showing it for years. One of the iconic figures, just like the Jovian auroral figure picture I'll show earlier. This is altitude on Venus. This Pioneer Venus orbiter data, by the way. Here's the magnetometer data. Here's the magnetic barrier. Sharp current layer there. So that's current layer, J cross B. Here's the thermal electron density, in this case, the Langmuir probe. drops, plasma scale height, and bingo, that is the boundary. Here's the external region, rapidly flowing. Here's the slow cold plasma. NKT in this region, all from data. You look at all the data, Langmuir probe type stuff, temperatures, RPA in this case for ion temperature. It balances the magnetic pressure, very close. And now, on the other hand, you enhance this field up to 100 higher, the whole ionosphere will get magnetized. It becomes much more subject to inputs from the solar wind, field line stuff, but you still want to approach it with MHD. And again, you give several talks. So again, the dynamics within the ion determine momentum balance again. Balance depends on EMN field forcing. Some of this could due to the link to that external plasma environment again, even though you're bookkeeping different. And again, the usual thing within the ionosphere, gravity, pressure forces, collisions. Pressure forces depend on electron and ion temperatures, and these do very much depends on the external inputs, particularly superthermal electrons. Otherwise, you get electron temperatures that are too cold. So there is important linkages. And plasma loss, as Joe Westlake was talking about, out the tail. Okay, and I'm going to run out of time, so this just shows yet another old figure showing the flow of plasma from day to night. This in the ionospheric dynamics at Venus from the RPA. Another interesting thing about this flow day to night, as well as the fact that it is strongly influenced by this external environment, is that it is a key source for the night side ionosphere on Venus. You carry O+ ions over, they come in to react with CO2 to force O2+, and there's some intrinsic ionosphere from electron, quote, precipitation due to Venus's, what did Melissa call it, puny aurora. That puny aurora is a source of plasma there, but so is transport from the day side. There are inputs and outputs there that are very interesting. Okay, really don't have time for that. Mars is, we're going to hear about Mars. I'm going to leave it to someone else. A lot of similarities to Venus, but mass loading is important due to pickup. The crustal fields are important. Mars, in many ways, dynamically is a bit of a mess, and there's a lot of interesting stuff. Someone also have to do it. Okay. Say a little bit more about Titan, since I'm involved in the Cassini ion and neutral mass spectrometer, and I'd be probably in trouble with Hunter Wade if I didn't say something about Titan in a talk like this. People can now report I did say something about Titan. 2 minutes, okay, that should do it. Here is almost the scale diagram of Titan. It's a cartoon, but it's really, here's a lower atmosphere, here's a thermosphere and ionosphere, 2,500 kilometer radius, you saw that from Joe's talk. You get to the bottom of the exosphere, it's about another 1,500 kilometers. It's really quite spherical. And then this exosphere and topside ionosphere. Titan is usually in Saturn's outer magnetosphere, sometimes in the magnetosheath. So there's this 100-kilometer plasma, not mainly O+, not N+, H+ protons coming in, carries Saturn's magnetic field and slams into Titan. And it's sort of mass loading effects help slow it down, but also pressure effects. It's a little more complicated than Venus. It's sort of both again. It slows down, and field lines are throughout the ionosphere. So again, acts as a conduit for outgoing plasma and incoming magnetospheric electrons. Down the tail, which we saw from Joe, was you have more energetic pickup ions, and you also have these chemically complex ions coming out the tail. This was made about a decade ago. Now, what is not shown in here is perhaps the complex topology that Joe was talking about, which is in and out of the plane, where you have this sort of two-lobe type things, and you saw almost polar wind type things. But dynamically, the interaction is very important. But so is sunlight. Both are important. Sunlight creates pressure gradients as well. So I'll see that. So that is important. I'll let Young John say something later in her own talk if she wants to. The way to approach this sort of thing is, again, not with a strong intrinsic field type thing, but with an MHD model. This is one of her earlier ones on Titan. She has several models which have done good work. You want to approach it with MHD. Okay, having said that, let me talk a little bit about inputs. Joe talked about outputs of ions. Certainly in the night side, inputs of plasma. Titan has a puny aurora too. You're going to regret that term, Melissa, but puny, but it on the night side is important for the plasma production. Electron precipitation is the dominant source of plasma on the night side. If you look in the outer magnetosphere, the CAP-CLS instruments see spectra like this. It depends on whether you're in the plasma sheet, in the lobes, or out in the magnetosheath. This is the electron spectrum. So it's a reasonably energetic electrons. Those will come down those field lines and create plasma in the night side, affect the energy balance, affect the momentum balance, affect the particle balance. That's MI coupling. So what this shows is that input, we put it in with a electron transport model and calculated the interplus production rate. We chopped it here because the INMS data stopped. We should have gone deeper, but we're very INMS centric in our group, and where there's no INMS data, we don't care anymore. Not strictly true, but anyway, for different field-like topologies, you see our model, and the things with the error bars are actually deduced production rates from a couple primary ion species seen by the mass spectrometer. They're in effect an effective product. And good agreement, that is the ion source on the night side for those cases. If we look at some other cases, these are again empirical production rates from measured CH3 plus and CH4 densities for the INMS. This is N2, by the way, N2 is the main neutral species on titan. Methane is the second most. So this is the key ion production rate in the ionosphere. These are magnetosheath electrons as measured by the CAPS, the bimodal and the plasma sheet electrons. And again, these are the dominant source of ions. And then I will, the 2 minutes is up, correct? Then I will move. Okay, no I don't. Okay, so anyway, these things do affect the dynamics. Here's empirical thermal and magnetic pressures. They drive plasma flows. We know that. But again, you're not using the intrinsic field to bookkeep. And I will go to the summary so I don't piss off the following speakers behind me.
This talk is open for comments, questions. Anybody want to, well, maybe you want to go back and tell us about the two or three slides you went over. That was so clear, nobody has any questions.
Okay.
You want to show us what you were rushing through?
Margie, Andy's got one. What? Wait. Andy, wait.
I mean, you implied that the night side ionosphere of Titan requires electron precipitation, well, some sort of impact ionization. Is that now clearly established?
Well, okay. Three things could contribute plasma to the night side of Titan. One, you could do it transport from the day side, right? As on Venus, except on Venus it's O+, which chemically has a long lifetime. On Titan, most of the plasma are molecular ions, and their lifetime is much less. I'm not saying it doesn't play any role. It probably plays some role for some species. But what the picture showed is that from the primary ions, CH3 plus, CH4 plus, which have very short lifetimes, we know what the ionization rate is. And it agrees with what you get by just sticking the measured electron spectrum down into the atmosphere. So it doesn't leave much room for anything else. Now, there are other situations where you probably do have ion precipitations, but not for the particular case I showed. So I think probably in the night side, electron precipitation is probably very important, probably the dominant. If you go deeper than that, I showed at 1,000, ion precipitation might start making a more important thing, might say not in the main ionosphere, but below the main ionosphere.
Jim.
Yeah, earlier you asked Margie where the hot electrons came from.
Yeah.
In Enceladus. It's these same electrons. They're brought in by interchange.
Now, of course, this is out at Titan.
I know.
Yeah.
They're brought in by interchange instability. They're brought into almost to Enceladus.
Okay.
Close enough. And that's where they come from. It's the same electrons.
Yeah,
The same electrons in the inner magnetosphere as we're seeing in the
It's the same,
outer
these same
magnetosphere.
electrons in the outer magnetosphere are brought in by the interchange
Okay.
instability.
Okay.
I see. Is there a question over there? Yes. You have to get a.
Just a note on the question that Andy had about the night side. There have now been some observations of the night glow at Titan. So now there is definite confirmation of precipitation that's showing that you're getting these electrons onto the night side to provide that ionization. Though you guys showed it first with the.
Yeah, I think it was by West et al. Or something.
Yep.
Yeah, so there's actually a visible aurora too.